Okay, so I would like to welcome everybody to this version of ChemHISTTalks from the Fall National Meeting. Our first speaker today is going to be Graeme Wyllie. Graeme was born in Balloch, Scotland, and he got his undergrad degree in chemistry at the University of St. Andrews before he moved to the United States and completed his PhD in bioinorganic chemistry at the University of Notre Dame under W. Robert Scheidt. He moved to Fargo for postdoctoral research at North Dakota State University and then jumped the Red River to Minnesota, joining Concordia College in the fall of 2006. His research focuses on designing new materials for the general chemistry laboratory program, including incorporating advanced instrumentation like HPLC and creating a semester-long course-based research experience. Graeme's talk today is called Glue and Adhesives, A Chemical History. Take it away, Graeme.
All right. Hopefully everyone can see that okay. Uh,
Yes.
and thank you very much for the introduction. So, my name is Graeme Wyllie. You might have noticed I'm a wee bit Scottish, and I'm going to be talking today about glue and adhesives. The inspiration for this talk is I was asked to present as part of a session in honor of Seth Rasmussen at the recent ACS, and looking about for inspiration, I happened to see many of my students basically gluing themselves to bioplastics, gluing bioplastics to the desk, and generally gluing anything that wasn't glued down in my teaching lab at the time. And I thought, I don't really know a lot about glue, so that would be an interesting subject to look into. So basically, if we're looking at that, what is a glue? So the definition is basically any kind of various strong adhesive substance, a hard protein, chiefly gelatinous, that absorbs water to form a viscous solution with adhesive properties, or basically a solution of glue that's used for sticking stuff together. And glue technology has been known for a very, very long time. What I wanted to do in this talk is try and think about how can I give a comprehensive version in under, a day's worth of talking. And so as I started to think about it, there is obviously going to have to be some limit. We can look at glues as simply very early humans going around finding materials that's sticky and going, can we use that to stick something else to that material? Examples of this would be pines and other resins, but this is not what I'm going to focus on in this talk. So as I tried to draw some boundaries on what I'm talking about today, what I really wanted to do is talk about glues and adhesives that have some significant manufacturing or basically human impact on their preparation. And so the veriest earliest example of these is going to be basically tars, which are found through the destructive distillation of birch bark. And here we're talking Middle Paleolithic period, examples 80,000 and 120,000 years ago from both Europe and Africa. And these are found through the destructive distillation of birch bark. So evidence for these has been found in various dig sites, and some of the archaeological history and archaeological chemistry literature has tried to reproduce the production of these, looking at things like various yields. The better they could control the temperature of the mixture for this destructive distillation, the higher the yield of the material they got, and also the composition. A lot of these are made from triterpenoids and other organic molecules that would come from basically reducing birch bark to kind of a tarry-like resin. From there, as we move forward, we're going to jump forward, and the next kind of material that was being used is bitumen, primarily a mixture of hydrocarbons with a smattering of sulfur, nitrogen, and oxygen. Early examples of this are the first types of a compound adhesive, where two different materials are being brought together. In this case, the bitumen itself is being loaded with iron oxide, and basically this is making a material that dries and can be used for making hafts and handles on sharp cutting materials. This is going to date back to about 60,000 years ago, and it's interesting that bitumen is one of the early constituents of this material, since as of today, there are still bitumen adhesives being used, especially those that require adhesive properties at very high temperatures. But then we start to move on and get a bit more animal in origin. Some of the earliest glues are based on casein, the protein found in milk, and this dates back to ancient Egyptians, Greeks, and Romans, used for gluing wood, gold leaf, sealing jars, And generally, the casein glue can be made by separating out the casein proteins or using samples like cheese and basically treating them with an alkali, such as limestone, lye, or whatever else is available in the presence of water, which makes an adhesive material which can then be used for gluing. It's also interesting that Theophilus Presbyter, the apocryphal author of Diversus Artibus, a book prepared around about 1100 to 1120 AD. Here includes one of the first detailed recipes of glue, which I've shown there in an excerpt from the Diversus Artibus. The casein glues are also kind of continued to modern day, and we'll come back to those later on. But of course, as we move forward through these, the main kind of glue that I'll be talking mostly about today will be collagen-based glues. These are extracted early on from boiling bones, skins, hides, sinew, and connective tissues, yielding a solid material which can then be used as a glue. Examples of this go back about 8,000 years. There are examples found in Israel and the area surrounding that, and it's used for decoration. There's some collagen examples shown on human skulls in the picture. It was also used for things like basket linings and also to attach pieces of various utensils such as knives. It's widely used in Greek and Roman times. The word collagen actually derives from colla or collops, which describes the thick neck skin of cattle. And the word for glue, I've also discovered from my next door neighbor here at Concordia, from Portuguese, is also colla as well, so related to that. Glue based on collagen was mentioned by Theophrastus in Inquiry into Plants, Book 5, where he talks about comparing different glues, such as from different plants and how it basically works to certain woods. It's also credited to Daedalus as the inventor of glue, perhaps not the best role model in Pliny, and it's used and mentioned by Dioscarides in about basically 90 AD as a medical treatment, so you can use it for treating of skin disease. There's also various literature, which I don't have time to go into today, looking at glues from fish and cheese at the same time. Collagen itself is basically a triple helix structure. It's amino acid strands, which are then basically coordinated together to give us the triple helix, which contain a very high percentage of glycine and proline. The structure of collagen, just to go forward in time a little bit, wasn't actually discovered until 1954 with a modification in 1955, where the actual idea of the triple helix, it was previously thought to be possibly an alpha helix, was come up with by Gopal Samudran Ramachandran, who basically is now credited with publishing it. People like Watson and Crick, and also various other investigators at the time, had looked into it, but the real first publication goes to Ramachandran. Making glue from collagen is very interesting. There is reports of a glue factory in Holland, which I've also seen mentioned as being apocryphal and what did not actually exist, around about 1690. And the first major text on the subject that I've been able to come across is The Art of Making Various Kinds of Glue, published by Duhamel de Monceau, who was a French botanist responsible for rebuilding some of the gardens of Paris and very active in things like grafting of various plants. He published a text looking at the arts of making various kinds of glue in 1771. Basically, glue itself continues to be made by basically reducing animal hides, horns, hooves, and other chewy bits, and basically obtaining a glue solution, which can then be concentrated through evaporation to form a jelly, which is allowed to dry. The picture you see is of an authentic animal glue. I was able to find this one on Reddit from someone repeating the old methods of preparing glue, and we can see it's quite a hard, brittle substance. This substance is then generally added to water, heated, and basically this gives us the material we can then use as glue. An early American glue factory advertisement is shown there, which ultimately would be sold to Eastman later on. The manufacture of gelatin is often hand in hand with glue, since gelatin can be obtained as part of this process. And it's interesting that it gets sold to Eastman because Eastman will be responsible for one of the synthetic glues later in this talk. As we start to get later on into the early 1900s, there's a number of texts now published in America. The glue book, How to Select, Prepare and Use Glue, was published by J.A. Taggart, a leather worker, and Sealing Waxes and Materials gives us an idea that this is a fairly larger kind of field. And there's also a number of other materials that would fall under it, but I'm trying to stick to just the glues here today. Looking at Taggart's glue book, he gives a kind of more detailed breakdown of how the glue is actually made. And by this point, the process is starting to become a lot more standardized. Obviously, obtaining the raw materials is an important part of this. And in the earliest days of glue manufacture, these would be come from abattoirs as leftover materials. Early on, there would be a contrast between using the hide for either making leather or for other clothing, or to use it to make glue. But as clothing production becomes a lot more industrialized, obviously more of the material is going to be available for making glue. The hides themselves are soaked in a lime bath, since it's mainly the layer below the hair and skin that we're interested in. And so that will allow us to dissolve away the hair, and it also allows us to saponify and remove all the wools and fats, because the presence of any kind of fat in the glue samples tend to make it greasy and reduce its adhesive power. After basically soaking in lime, the stock is generally washed prior to boiling, and then it's boiled for 8-hour portions in a liquid. Samples of that liquid are then collected off and cooled, and if it forms a stiff jelly on cooling, the runoff is the liquid is then run off. Basically, the vat of skins and residue is refilled and boiled again, and the runoffs are cooled in 6 by 2 feet troughs generally to obtain the glue, which can then be washed out of the troughs, basically using a flow of water. Fortunately, it doesn't have any of the organic materials, but basically a couple of pictures from obviously a highly popular tourist guide, A Visit to the Glue Factory, show the washing tumblers. And then in the picture on the right-hand side, we can see the glue cooling trays and then the boiling pans themselves there. So that kind of shows you some of the production of glue. As we start to think about this more from a chemist's point of view, one of the seminal works that comes out is published around about 1900, which is Glue and Glue Testing by Samuel Riddell. Riddell's more famous for his work Water and its Purification, looking at basically how to obtain pure water and clean drinking water. And basically, he published this volume. Unfortunately, I have not been able to find a picture of him at this time. While a lot of the work does compile work by earlier scientists, this is a really nice piece that brings everything together and also starts to talk much more about the chemistry of the glues instead of simply glues being made and their properties being measured from a usage point of view. He recognizes very early on that glue and gelatin are often used interchangeably, not strictly defined. And when the glue is being processed, gelatin is often obtained, since it occurs from the hydrolysis of collagen and can be collected in the earliest fragments and purified into a very pure gelatin-like material. A lot of the glue from the later contains gelatin, smaller collagen fragments, and other materials as well, possibly some elastin and some keratin as well. But Riddell tries really hard to kind of break down what's actually going on and analyze what is in the various glue samples. He also talks about he also carries out things like elemental analysis on the various glue samples and provides a very good picture for the time of the different processes that happen upon the hydrolysis of the collagen leading to gelatin, and then that can be broken down further as well. Interestingly as well, he also talks about basically the glue testing from a chemistry point of view, basically how to physically test glue, which I thought was a very interesting chapter, starting with drying, smelling, tasting, not something I would be too keen on doing, and its keeping ability under moist conditions, as well as chemical examination, looking at water content, the amount of ash, since often glues were contaminated with various minerals and inorganic materials, looking at acidity, insoluble materials, and determining the gelatin. Also, he points out that determining the amount of nitrogen using the Kjeldahl test and multiplying the result gives a good way to estimate the amount of gelatin and collagen in the actual glue itself. And that multiple is shown by analysing various samples. Of course, it's not just horses and cows, and glues can also be made from fish. In the case of making collagen-based glues from fish, that's given the material name isinglass, and these tend to be more transparent, lighter materials. A very well-known example was Lepage's liquid glue, or a mucilage, which basically was made from fish glue and came in these characteristic bottles, which I think some of our older members may recognize from when they were younger. And not just keeping it to animals as well. Around about this time, we can also make glue from plants and basically various polysaccharides. Gum arabic is a very early example. 70% of the gum arabic is harvested from tree sap in the Sudan, and it's used as a binder for paints, stamp adhesives, especially in the UK, and often to hold things like gems in place. It's also one of the edible glues and related to another material, dextrin, which is made by the treatment of starch with nitric acid. This was used more commonly, in case you're wondering, as the adhesive on a lot of the early American stamps. And so basically, this was a very common adhesive in the United States. It's interesting it comes about from the treatment of a polysaccharide with nitric acid, since that leads us nicely to when we start to get into synthetic and much more man-made adhesives. And the first example of these has to be collodion. Discovered by Louis Nicolas Menard and Flores Dumont, and thank you, Greg, for sending me some background on the latter this morning. This is a material which was made initially by dissolving nitrocellulose in a combination of acetone and ether. Originally, the experiments were carried out in 1846 by the two. Menard goes on to become, as he self-describes, a pagan mystic and writes his memoirs in 1876. But for a brief while, he dabbled in chemistry and is responsible for the dissolving of nitrocellulose in acetone and ether to make this collodion material. Is it useful? It's still being used to this day. So over 180, almost 180 years on, it's still being used. If you have ever had ECG electrodes attached, this is still the material being used for that. And it's also used for scar glue, wound dressing, and various other processes as well. It was used commonly in photography for a long time as well during that period. The name, interestingly, didn't come about till about almost 20 years later, given in a publication by John Menard, a Boston doctor, who basically started reporting the usage of this as a medical material. And it was his colleague, Dr. Gold, who actually came up with the name of collodion, which he translated as essentially gluey. And so that's where the name comes from. Remembering this is basically nitrocellulose dissolved in various solvents, it leads us to the first commercially available adhesive, which is Karlson's Klister. Originally developed by Axel Karlson, who was born in 1892, he was sold, or at least boarded out to another family of bakers, and was able to grow up experimenting with various flour glues and also working in the cinema. The cinema is the interesting one because basically the availability of celluloid, nitrocellulose treated with camphor, and he was able to dissolve this in acetone, which gave a very strong glue, but dried too fast to be useful. Later in his life, as we got into the 1920s, he started to develop and perfect his recipe and basically came up with a material that could be used as an effective shoe and stocking repair glue. But unfortunately, he didn't patent it. And so it was patented by his partner, who basically then bought the company and ended up employing Karlsson as one of his workers. This is recognized as the first synthetic glue on the market, and in Sweden is very, very famous for the donkey motif, which was on all of the marketing materials. Karlsson himself moves to the US, to Rockford, Illinois in 1927, basically founds a company to manufacture his Klister again, which ultimately becomes purchased by Testor, who are still going to this day, and produce something called Karlsson's Klister, although the recipe has changed quite significantly. Karlsson himself returns to Sweden in 1929. The Testor company, however, is still going to this day. After he returns, he marries changes his last name, becomes a boat owner, a teacher, an inventor. He makes rotatable greenhouses to take advantage of the more limited sunshine, and then also develops wood glue formulations working for the Johnson Company, and ultimately passes away in 1977. But very famous for the first commercial glue on the market. As we continue through the 20th century, we of course get to the Elmer's glue. The earlier Elmer's glue, however, not being a mixture like they are today of polyvinyl acetate, alcohol, and propylene glycol, instead consisted of casein, which you'll remember dates back to the ancient Egyptians, Greeks, and Romans. That also explains why the cow logo is on, since they were often the company that basically owned Elmer's before the name change, basically owned dairies as well, which was the source of the casein for the making of the milk. These are glues that basically work through evaporation, leaving behind adhesive residues, and obviously picturing Fritz Klatz there, who is the discoverer of polyvinyl acetate. Moving onwards, also hot melt adhesives date from the 1940s. Developed by Procter & Gamble. Paul Cope is credited for these, and these are very suitable, the kind of thing you would find with your hot glue gun for use in high humidity environment. These are not ones which are rehydrated, since obviously we want to work in high humidity here, and instead consist of two kind of major components, polymers, ethyl vinyl alcohol mostly, and tackifiers, which commonly are terpenes, which we've seen several times before. They're the active sticky material in a lot of resins and also in our beech bark distillate as well. But as we kind of get into making more of a synthetic adhesive, we start to get into cases where we're not looking at using the polymer in the glue formulation, but rather forming the polymer as the glue operates. And the first major example of this is going to be epoxy resins. The earliest examples focus on reacting epichlorohydrin, shown there, with bisphenol A in a caustic environment, making the diglycosidyl ether, which can then basically be used as an adhesive. Very low viscosity. They're easy to use, fast curing, a very low shrinkage, and a high adhesive and mechanical strength. The early work on these builds upon that of Paul Schlack, who reported in 1933 a very low molecular weight compound from reacting epichlorohydrin with bisphenol A, but taking it to the level of actually making a commercial resin is done by two people independently a couple of years later. Pierre Castan produced a low-melting resin in 1936 in Switzerland, which would then be later licensed to Ciba, while independently DeVoe Reynolds' company, Sylvan Greenlee, pictured on the right here, basically synthesized a range of resins from the epichlorohydrin and bisphenol A, and together they're both essentially credited with the discovery of the epoxy resins as adhesives. Both of them patented independently, and there are examples shown of both of their patents there. And moving onwards, of course, keeping this talk going, we'll of course have to mention the cyanoacrylates, also known as superglue. Originally discovered in 1942 during attempts to make transparent gun sights during the war, which basically resulted in a material which was sticky and absolutely unusable for what they wanted to do. They were then revisited at Eastman, if you remember the earlier glue factory, in the 1950s in the attempts to make a jet canopy material that was transparent. Again, it resulted in what could be described as a sticky mess, and basically somehow decided this has possibly potential as something adhesive rather than trying to make some kind of transparent like plastic. The earliest super glue is brought to the market as Eastman 810, and as many of the different materials advertisements show, the goal of advertising how strong your product is simply to take something heavy like a car, attach it to a piece of super glue, and then prove that you can lift it. Early epoxy resins using araldite also used similar kind of advertisements as well. Super glue itself works through a polymerization. The cyanoacrylate in the presence of water polymerizes and basically gives us the long polymer shown here, which then basically serves to adhere the two surfaces together. The discoverer credited for this is Harry Coover, born in 1917, who graduated with his master's and PhD from Cornell, although the latter was basically looking at commercial synthesis for vitamin B6. For his work in the discovery of superglue, he won the National Medal for Technology and Innovation in 2010 and sadly passed away in 2011. And that's kind of gives us an overview of most of the major adhesives. With only 25 minutes to go, I've obviously tried to abbreviate, but where are we at looking forward? When I originally gave this talk, the CNE News, as I was pulling this together, there was an article in CNE News looking at green glues, and there's also a large amount of other literature being published on the idea. As we start to look at how basically glues from things like barnacles and other organisms which have adhesive properties, or slime, hagfishes, for example, can we start to make glues from these materials and move away, in some cases, from the petroleum-based super glues and adhesives? I think that's about all I've got. I want to do a couple of thank yous. Seth Rasmussen, this talk was originally given in his basically award-winning symposium session at the Fall ACS meeting. Great Lakes Regional Meeting 2025 and the ACS Fall 2025. I got to practice and give this. The history division have been absolutely invaluable in welcoming me in, encouraging me in looking at these things. And Concordia College Library and the Hathi Trust have provided a lot of resources in trying to find some of this literature. That's all I've got. I'm happy to answer questions. And I just kind of finish awkwardly.
That's okay. All right. Does anybody have any questions? I think you can
Throw them in the chat.
throw them in the chat, or you can just unmute and ask your question. Anybody? Oh, I see
there's a hand waving.
hands clapping. Yay.
Well, I've got my hand up. First of all, I'm glad that I caught this, Graeme. I didn't have a chance at GLRM. Thank you. Very interesting. Now, I've got a question. Have you looked at all at the 20th century history of formaldehyde-containing adhesives?
See, the joy of giving this talk is every time I basically give it, someone brings up something that I'm aware they are there. So I know they predate the epoxy resins, and I do have a little bit. I had to cut some corners, but I have looked at them a little bit.
Okay, and the other question is, did you come across anything in your work on this in the archives and the original materials about the degradation of these nitrogen-containing adhesives by microbial activity?
I haven't on that one, though.
Because currently there are some nitrogen-containing adhesives, and in the standards for those, when they're used, especially in structural applications, must do microbial degradation tests to assure that the adhesives do not degrade in use from particularly bacterial, but also fungal action.
Yeah. I know, going back to I mentioned the work by Ridiel, I know that's one of the other things they talked about in the tests is keeping ability in various conditions and also in the presence of basically mold. There was a lot of concern in the books, the Taggart book and several of the other books, even and then they're concerned about basically microbial and basically your glue getting moldy.
Yeah.
It contains just enough water, and if you store it in moist conditions, it's essentially a growth medium.
Exactly. And before I get too far in monopolizing the questions, are you willing to share these slides? And would you like to give this talk to the UPLS at some point in the new year?
Sure, and I think we'll do it through the speaker directory so that my bosses at LSA can get the what do you call it, the check mark for it. So I'll put it in my speaker directory one, and then you can invite me through the speaker directory.
All right, and can you send me the slides?
Yep, I'll get them to you at some point.
All right, thank you very much. Appreciate it.
Yep.
Again, I enjoyed the talk.
Thanks.
Okay, thank you, everyone. And I'll again remind you, these will be posted on the HIST YouTube channel. If you were looking for that link, you can find that on the website in about 24 hours. I'd like to introduce our next speaker is Greg Girolami.
Yep, I'm gonna
You're going to unshare your
sharing. There
screen
we
while
are.
I do my talking. Greg received his bachelor's degree in chemistry and physics from UT Austin and a PhD from University of California at Berkeley. He joined the Illinois faculty in 1983, and that is where he still is as a professor of inorganic chemistry. His research interests involve synthesis, properties, and reactivity of new inorganic, organometallic, and solid state species. He is talking about something completely different today. And so the title of his talk today is Remarkable but Little Known American Contribution to the Invention of the Periodic Table, the work of Charles F. Chandler and Charles S. Pierce. Greg, take it away.
Thank you. Yes. So as was true for Graham's talk, this also is a talk that was given at the ACS meeting recently. And this was the title that I originally submitted, and I mentioned in my talk at the ACS meeting that there are sometimes dangers submitting abstracts before one has completed the scholarship or the talk. And in this case, it turns out that there is a change that I discovered in the course of finalizing this talk. And so I'll leave that as a mystery to be revealed in the course of the presentation today. There's been a lot of scholarship on the early developers of periodic systems, in other words, predecessors to Mendeleev and Lothar Meyer, who in 1869 introduced what are really the very first comprehensive periodic systems. Among these earlier developers was the French geologist, really, Béguier de Chancatois in 1861. There was also work by English chemists William Odling and John Newlands in 1864. And Lothar Meyer also in 1864 had published a preliminary version of his system in a book. Among American chemists, there are a couple of contributions that are known. One by a Danish-American, Gustavus Hinrichs, who in 1867 and 1869 published two different versions of his system. And after 1869, 6 years later, Lewis Gibbs published what he called his Table of Chemical Elements, and probably independently of Mendeleev, because nowhere in his paper does he mention Mendeleev, although he does mention some of the other predecessors that I just talked about. Now, I thought I knew a lot about the history of the periodic table, in part because Carmen, Junta, and Vera and I had put together this symposium in 2020, I guess it was, or 2019, on the 150th anniversary of the periodic table, followed up by a symposium volume that Seth Rasmussen helped to put together. And in one of the books I have that I often have read about the history of the periodic table was a book written by the North Carolina chemist Francis Venable in 1869, a title page which is shown here. And although I've read it many times, there was one thing that I ran across recently that spurred me to do a little bit of further investigation, and this was this paragraph in Venable's book, where he mentions an anonymous paper that appeared in 1869 in the American supplement to the London Chemical News. And in this description, Venable says that the paper considered the parallelism of the elements in a different way from the double parallelism of Dumas, and in a broader sense, though the ideas do not greatly differ. And there's not a whole lot else that's given here, but it was enough to spur me to take a closer look at this. This paper, as Venable says, appeared in this American supplement to the London Chemical News. Actually, there were three papers. The one Venable is mentioning here appeared in June 1869, and it was in response to papers that had been submitted in two previous issues in April and May of the same year. So the structure of this talk is as follows. I'm going to talk about what was the American supplement to the Chemical News, where these papers appeared. What was the content of the three papers in 1869? Who was the anonymous writer of the June paper? Because Venable says it was written anonymously. Did this paper describe a periodic system? And who was the editor that wrote the April and May papers? Because it turns out there are two people that are involved here, and what previous scholarship exists on these papers. So let me turn to the first topic here, the American supplement to the Chemical News. Well, the Chemical News was a long-standing periodical in Britain from 1860 to 1919, edited by William Crookes, a polymath who was known as the discoverer of thallium, or the co-discoverer of thallium. He invented the Crookes tube, which was an improved Geissler tube for investigating electrons in vacuum, and also invented a radiometer, this little almost toy, but it really wasn't, where you had spinning vanes whenever the vanes were illuminated in light inside evacuated glass containers. The Chemical News is actually where Newlands published his Law of Octaves in 1864. So it was a place where all sorts of information, both theoretical, experimental, and practical, was published for many, many years. For 2.5 years, from January of 1868 to June of 1870, the Chemical News, as published in Britain, was no longer sold in the United States, and instead there was an American version called under the same title, which was the American reprint. And this appeared, usually articles appeared a few months after the original articles appeared in the Chemical News. And here it says it's the authorized American reprint. And as I said, when this preprint started, the London edition was no longer sold in America. The reason for it was that there's an American publishing firm called Townsend and Adams that actually paid Crookes a royalty to publish this American reprint. And so they got exclusive access to the American community by agreeing with Crookes that the British version would no longer be sold in the United States. And in the first issue of this American reprint in January 1868, it says the numbers of the reprint may henceforth be expected to be as close a facsimile of the English edition as the case will admit of. The mechanical execution of the American edition will not, we are confident, suffer any disparagement by comparison with its original. So it was this firm of Townsend and Adams published a small number of scientific and medical journals during the late 1860s, as well as manuals on hunting, horse breeding, harness racing, but went out of business in 1870 at the same time that this American reprint was discontinued. The American reprint was printed from completely reset type, and the supplements, and so I'll talk about that. So starting in about a year later, the reprint included not only articles that had appeared in the British version, but also articles that were new, that had an American flavor. This was called the American Supplement. It's usually about 4 pages long, written by an American editor, but there was no byline, as you can see here. And it says that the supplement is intended to be made up of Chemical News, which it is impracticable to obtain by way of England, and which we limited almost exclusively to American affairs. Okay, so let me turn now to what did appear in this American supplement that was this column in the American reprint of the Chemical News in these three issues. So this is the first of the 3 papers. Again, it appears anonymously. There's no signature attached to this. And it's pretty clear, though, it was written by the editor of this American supplement. And it says here that in the following table, the elements are arranged in 2 columns according to their even or odd atomicities, which is valence, and at the same time observing the order of their atomic numbers. And although this refers to atomic numbers, really what's meant here are atomic weights. And so you can see that in this, that what's happening is that let me see if I get my pointer here, laser pointer, right? So that these are the ardiads, which are even valence elements, and the perisads are odd valence elements. These are terms that had been introduced in 1864 by someone I've mentioned already, William Odling. And so in this, the anonymous editor pairs glucinium, which is beryllium today, with lithium, carbon with boron, oxygen with fluorine, etc. And so he's pairing elements that have an even valence number, oxygen, for example, being 2, with an odd element with an odd valence, in this case, say fluorine being a valence of 1. And continuing on through elements, the last one being thorium. Okay. The editor goes on to say that an inspection of the table shows that elements are brought into something like a natural relationship, and there's a correspondence to the atomic numbers within each pair. Each pair of the atomic numbers are very similar. And so he then shows that there are groups of these elements that one can abstract from the longer table. So for example, these which we now refer to as the alkali metals, lithium through cesium, can be paired with elements that we refer to as alkaline earths, okay? And also that the halogens, from fluorine through iodine, can be paired with the chalcogens, oxygen through tellurium. And you can see there's a similarity in the atomic numbers. And he also notes some other similarities between some of the transition metals, silver, gold, lead, with palladium, platinum, and thallium. And makes some further comments in this first paper. The peculiar relationship of the ardiads and perisads in the table is very striking. On one side are all the metals of the known alkalis, and each is paired with a metal of a well-known alkaline earth. Moreover, on each side, there's a plain progression of the properties in the order of the atomic numbers, the periodic trends that we know on descending a column, he's pointing out here. But there are many ardiads which have no corresponding perisads, and it is very noticeable that so many of these occurred together. And he says, is it possible that these vacant places are to be filled by the discovery of new elements? And although a few of the predecessors to Mendeleev, Lothar Meyer in particular, had glimmerings that maybe vacancies in their tables might correspond to new elements. The only one who, apart from Mendeleev, who explicitly articulated this before Mendeleev's publication in 1869, is in fact this sentence right here. So this is an independent proposal that these numerical regularities might signal the invention of the discovery of new elements. I should take that back a little bit. This is in the context of what I would say is a periodic system. There were a few people, someone by the name of Lenson, who also had speculated that maybe there might be elements that one could discover by looking at these sorts of numerical trends. If the theory here is suggested as tenable, we may continue the search for new elements with confidence that we may know in advance something of their nature and properties. And again, this is something that Mendeleev did very successfully in making predictions of the elements scandium, gallium, and germanium later this same year. This is then the May issue. This is the next issue of the Chemical News, and says that comments that the pairing does not appear to be the result of any of the known properties of matter and is thus a new and independent phenomenon. Any arrangements based on it and consequences deduced from it may therefore stand alone. And in the beginning, he says here, this pairing could be a new confirmation of the modern atomic weights. In other words, that the atomic weights that have been determined experimentally for the various elements, now there was a possibility of an independent confirmation that those numbers were right by virtue of the pairing that was suggested by the editor. So not just a standalone fact, but something that could be woven into a larger framework to see whether the atomic weights are right. And of course, Mendeleev took advantage of this by proposing corrections to some atomic weights on the basis of the fact that the originally assigned atomic weight put it in a place in the periodic table, his periodic table, which didn't make sense. Venable said these papers considered parallelism of the elements in a different way than Dumas, though the ideas do not greatly differ. And here's a table from Dumas' paper from 1857 and 1858, which is, again, shows this kind of pairing, in this case between the halogens and not the chalcogens, but rather the nitrogen elements, and between the alkaline earths and the chalcogens. So these are different pairings that are in the papers we're talking about here, but nevertheless Dumas is pointing out that there is a constant difference in the atomic weights, here of 5 and here of 4, for these two different groups of elements. Dumas did not talk about valence at all. So one difference between what Dumas did and what this anonymous editor did is the anonymous editor explicitly considered valence as one of the principles in producing these pairings. Now we come to the June issue, which is the one that actually is the most interesting. And in this letter, this is the beginning here is what the editor says, is of the letters which we have received upon the subject, the following is the most important. And the quote here, the remarks on the atomic weights in the April number of the Chemical News have suggested to me, now this is the letter writer, the enclosed table. You perceive that I've put the different elements at heights representing their atomic weights, and those of one series, in other words, the even valence elements in columns together, and the odd valence elements in columns together as well. You will perceive, however, that the atomic weights seem to arrange themselves on the diagram in parallel shelving lines, and I'll show you the table in just a minute. And also there is a correspondence between the series of ardiads and piracids, which have the highest atomic weights, that is to say, the alkali metals, including thallium in this case, on the one hand, and the alkaline earths, including lead, on the other, inasmuch as they have similar chemical properties, and he lists some of them here. So here's the table that appears in this June 1869 issue of the American supplement, of the American reprint of the Chemical News. Piracids, again, the odd valence elements on the left, and the ardiads, the even valence elements on the right. And the shelving lines, what he's referring to are these groupings of elements where you can draw slanted lines through elements that have similar atomic numbers, atomic weights in this case. Okay. So the increasing atomic weight increases from bottom to top, and we can assign valences to the various columns here, although these are not explicitly included in this paper. For example, all the alkaline earths rather have valence of 2, and the alkaline metals have valence of 1, etc. On the previous page, this letter writer had noted that this group of elements, the alkali metals, can be paired with the alkaline earths. So I'm just showing this relationship here. And in following text, the letter writer points out that there are correspondences between the halogens, which was pointed out by the editor in the April issue. Here are the halogens that can be correlated with the chalcogens, okay? And so they lie in his diagram on opposite sides, but equidistant from the center line. Also points out this correlation between the nitrogen elements and the carbon elements. So here are these relationships also drawn in the diagram. What's interesting is that these were the only correlations that were discussed in this paper. And with modern eyes, you can take a look at this and say, well, there's a lot more that one could have done here, but that wasn't done. So for example, one could have suggested that zirconium and titanium, these two elements that were here, could have been paired with elements that also are not in this group, but which are elements that niobium and vanadium. And so they also seem to be paired, but that correlation wasn't made. In vanadium, we know that these elements, of course, are in neighboring groups in the modern periodic table. And also that there was no partner for arsenic. So we could have proposed, for example, that germanium, an unknown element, might remain to be discovered, and you could have made some prediction about what its atomic weight would be, and also some of its properties. For example, that it would be tetravalent, have a valence of 4, but that wasn't in this particular particle. Okay, so let me now turn to. I'll come back to this table, but let me now turn to who was the anonymous writer of the June paper. And that actually has been known for a while. So the writer was, in fact, an American by the name of Charles Sanders Peirce. And Peirce's library still exists. And in fact, this is his own copy, annotated by him with his initials, CSP, showing a copy of this same paper from the June 1869 issue, and marking that the text starting with this quotation is due to him. And then later where he comments on the table, he says the table by me, CSP. Here's an image, photograph of Pierce. Now I'm going to say this. I found this description of him, but I'm going to come back and sort of take, at least counterbalance this. Pierce was a strange and unruly man. He was a crank. He was arrogant. He was his own worst enemy. In an obituary notice, his nephew wrote, he loved and hated and quarreled with almost everyone he came in contact with. He thought to make a bundle by his investments and lost what he had. Although a Northerner, he did not believe that slavery was bad. And in this respect, he duplicated the opinions of his father. He had unconventional views about religion and theology. His fury could be uncontrolled. In 1889, he pleaded guilty to assault on a servant girl. And in 1895, he was a fugitive from justice. There were conjectures of adulterous affairs, and he was given to drink, and he experimented with drugs by way of self-treatment. And I hope my obituary is not quite as colorful as that. Let me tell you a little bit about Pierce. He was born in Cambridge, son of a very well-known mathematician, astronomer, Benjamin Pierce, and Sarah Hunt Mills, who was the daughter of a senator. He earned the first summa cum laude Bachelor's of Science Chemistry degree from Harvard's Lawrence Scientific School. He was intermittently employed by the U.S. Coast Survey, later called the Coast and Geodetic Survey after 1878. He was assistant at Harvard's Astronomical Observatory and wrote a book called Searches, and was appointed lecturer in logic at Johns Hopkins in 1879. He's best known for his work in philosophy and logic and known as the father of pragmatism. And in fact, he was and remains a very influential philosopher, is known and admired for his voluminous published work on an amazingly wide range of topics. In addition to chemistry, he wrote on mathematics, logics, physics, geodesy, spectroscopy, astronomy, language, communication, the theory of signs, psychology, anthropology, history, and economics. And so he's actually quite well known. At Harvard, he had been a student of Josiah Parsons Cook. Now, this is not Crookes. This is a different person. Josiah Parsons Cook, longtime professor at Harvard, who in 1855 had contributed his own ideas about the classification of elements and finding numerical relationships between the atomic numbers of elements that are chemically related to one another. It's not a periodic system because there was no attempt to correlate elements in different groups, but nevertheless, one can see in Pierce's contributions, his table, some linkages to these ideas. This paper described a periodic system. I'll briefly talk about this. So here's the table, and I'm going to do some manipulations on it, which are a little unfair, but I think still an interesting way to take a look at this. So let me just duplicate it here. Let me turn it upside down. So now the atomic numbers increase from the atomic weights, rather, increase from the top to the bottom. Let me turn the labels right side up. And now what I'm going to do is I'm going to take this version and I'm going to fold it across. So I'm going to superpose the elements on the left with the elements on the right and no longer distinguish left from right in terms of the odd versus even valencies. And when I do that, I come up with this. So again, this is not something that was done in the 1869 paper, but I think it's interesting to show just how close this table comes to the modern periodic system. So if I take away the duplicates, we can now really see that there's a first main group row here from beryllium through fluorine, and then the second group, the transition metals here. There's a third main group, at least partial here. Second transition metal series, and then sort of scattered lanthanides are not included at all. But one can see that there is a ordering of the elements that does mimic what we now include in modern periodic tables. In a sense, this table does have some resemblances to the table that was put together by Béguier de Chancatois in 1862 in similar sort of slanted lines. The difference here being that this x-axis here, so the y-axis is atomic number and atomic weight in both cases. The y-axis here, or the x-axis here, is the atomic number, atomic weight modulo 16, whereas here it's really more valence rather than atomic number. So now let me turn to the question whether whether Pierce's system was in fact a periodic system. Well, it does have some of the aspects that we expect of a periodic system. In particular, that there are not only relationships between the atomic weights and other properties of elements within a group, but also such relationships between elements in different groups. So it has this kind of two-dimensional character that is the essence of the periodic system. And one can consider the system to consist of significant fragments of the more integrated periodic table proposed by Mendeleev. But it's notable that despite the fact that the system was somewhat fragmented, it still was possible for them to propose that there were elements left to be discovered because there were certain elements that didn't have a partner that was expected based on the correlation. So, and in fact, that one can make some predictions about the properties of these unknown elements based on these periodic trends. The system is, however, though, not a true periodic system in the sense that because it was split between the even and odd valences, and this meant that many of the aspects of the periodic system that we consider today, where it's a linear trend in terms of atomic weights, really is not characteristic of this system. It sort of is, but only in sort of segmented series. But it does have the two-dimensional character, and as I showed, if you simply lay the left and the right-hand sides on top of one another, then one does see expressions that are very much like the full periodic table as we know it today. So now we turn to the question, who was the editor who wrote the April and May papers? And there was some uncertainty. In fact, I was quite uncertain when I got into putting together this talk, because at the outset, it seemed pretty clear that it was a chemist by the name of Charles Frederick Chandler, because I found in his obituary, his biography in the biographical memoirs of the National Academy of Sciences, the quotation, "As an editor, he supplied for several years an American supplement to the monthly edition of the Chemical News." And since this American supplement only lasted a very short time, if he was editor for several years, that seems to cover the entire period of its existence. And in fact, one can find advertisements from 1869 about the Chemical News where it says that it was edited by Professor Chandler of Columbia College. I'm going to briefly go over, only briefly go over his biography. He studied under Josiah Parsons Cook at Harvard. He got his PhD in Germany. But for most of his career, he was the chair of the chemistry department at the Columbia School of Mines. Most notably, though, or more equally notably, he was president of the American Chemical Society and was one of the co-founders of the society when it was established in 1876. And he was known as the father of modern sanitation. But then I found this. In the December 1868 notice to readers in the American reprint of the Chemical News, this says that this is where the American supplement was first advertised, and it says this new department, this column that was in the American reprint, will be under the editorial charge of Professor Charles A. Seeley, of New York, a gentleman abundantly qualified to execute in the best manner the task thus undertaken. And here's a picture of Professor Seeley. He was known for a number of things. He discovered a process for making carbolic soap, for preserving wood, for making grape sugar, making hop extract, and machinery used in some of these processes, and designed dynamos to minimize energy loss in electrical systems. He did a quite large number of things. Here's a more complete listing of his life. He was born in 1825 in New York, near Albany. He was educated at Rochester Collegiate Institute, now part of Rochester Institute of Technology. Got his bachelor's degree at Union College in Schenectady. He was a writer for the Scientific American starting in 1853. He founded the American Journal of Photography, which from 1855 to 1867. professor of chemistry and toxicology at the New York Medical College. And so this is immediately before he started to the editorship that I'm going to talk about. He founded a number of short-lived companies to make dynamos and photographic chemicals. He was the chair of chemistry at the New York College of Dentistry in the years we're talking about. He was a chemical expert in patent litigations later in his life, and he died at Mount Vernon in New York City. And I was able to find eventually proof that, in fact, he was the editor that was responsible for the April, May, and June issues of the Chemical News. Because here's a news item from a periodical called the Round Table from May of 1869 that talks about the American supplement edited by Professor Charles Seeley, and talks about the May number, which is one of the numbers, one of the issues that where these three papers appeared. I then found in a different periodical in July of 1869, so this is after the last of the articles, which appeared in June, that with the July number, the American reprint of the Chemical News will continue the American supplement, but this column will now be under the editorship of Charles Chandler. So he took over in July, which was a month after the last of the three papers that we're talking about here. Okay. I'm going to finish then with what previous scholarship exists on these papers. I mentioned that George Kaufman had listed this in a paper that he had written. There are a couple of other times that these papers have been discussed, perhaps most notably in the PhD thesis of Christopher John Campbell from University College London in 2017. This thesis is mostly devoted to the chemical aspects of Peirce's philosophy, or how chemistry informed his philosophy. And in the thesis, Campbell does discuss this paper, particularly Peirce's contribution to the last of these. But I would say it's descriptive. It isn't analytical. It merely quotes some of the text that are in Peirce's letter without really going into any analysis of it. Similarly, in 2010, Helia Krau published a paper on a completely different topic in the Bulletin for the History of Chemistry, where he mentions this periodic system by Peirce, this paper that he published in 1869. Perhaps most notably, Krau concludes, although Peirce's pairing scheme of the elements has not attracted attention among historians of chemistry, it clearly has a place in the history of the periodic system. So let me conclude. The American chemist Charles Peirce constructed a periodic system in 1869, and I give some of my reasons for believing that it is a kind of periodic system, although a somewhat fragmented one, because it does arrange elements with analogous properties into groups, and these groups then their relationships between the groups that are recognized, so that there is this two-dimensional character that I think is the essence of the periodics of any periodic system. It was based on a two-dimensional array in which the x-axis was valence, separated even and odd, and the y-axis was atomic weight. His system, I think, certainly was less developed than those of some of the other people who developed periodic systems in the 1860s. In some respects, was more advanced than that of Béguet de Chancatois, but certainly worth comparing with the systems put together by these other chemists and scientists. But I do agree with Krau that Peirce's scheme clearly has a place in the history of the periodic system, but I would give Charles Seeley, the editor, co-credit for pointing out that the pairing of the elements with even and odd valences had some regularities which stimulated Peirce to assemble the pairs into a larger system. With that, I will thank you and congratulations to Seth, for whom this talk was put together, and I want to thank you for your attention today.
Thank you, Greg. That was a great talk. We don't have time for any questions, but if anyone has a question, I'm sure you can contact Greg directly and he'll be happy to answer those questions. Thank you, Graeme, again, for giving a wonderful talk. And thank you to all of our listeners and viewers who have joined us for today's ChemHISTTalks. I hope to see you at the next one. Bye.